Hi there. Most of the next few videos will be about vectors, so perhaps it would be best to start by saying a bit about what a vector is. And in order to do that, I should first tell you what a scalar is. So a scalar is, like most of the numbers you've dealt with in maths at school and at university up to now, it's got a magnitude, it's got a size, but it's got no direction. A vector, on the other hand, is like a scalar in that it has a magnitude, but it also has a direction. So a vector consists of a magnitude plus a direction. Because the real world has 3 dimensions, all the vectors we talk about in this course will be 3-dimensional vectors. But it's nice to be able to draw pictures of vectors, and the blackboard's only 2-dimensional. But we do that anyway. We just draw pictures of vectors and on the blackboard, and we just have to remember there's another dimension in the real world. So, for example, we might draw this vector. I put a little arrow on it to say which direction it points in, and I might give it a name. I might call it V. Now, it's very normal that when we label a vector, it's nice to know that it is a vector. And so the normal way of doing that, at least on a board, is to underline it. So I'll try to underline all the names of my vectors. Now, the start and end points of a vector are really not important. All that matters is the magnitude, its size, and its direction, which is up in this direction here. So it's the same as any other vector with the same magnitude and direction. So in particular, it's about the same as this vector here, so I'll also call V, because even though they have different start and different end, they've both got about the same size and about the same direction, or at least as close as I've been able to draw it on the board. However, V is really different to a vector with the same magnitude and a different direction. So V is different to this vector I'll call U. Even though V and U have about the same size, they point in a completely different direction, so they're a different vector. Similarly, V is different to this vector here I'll call W, because even though they point in the same direction, they've got a completely different magnitude. This vector V is quite big, this vector W is very little. I should also tell you now about one special example of a vector, the zero vector, which I'll draw as a point, and I'll name it 0, underlined of course. Now the zero vector is kind of special because it's got no size, so you can't really tell which direction it's pointing in. Maybe it doesn't matter, you might like to think. But you see it again and again, it's a very important vector. So throughout this course we'll have to be combining vectors in various ways, and the most common way of combining vectors that we have to use is adding them. So, what does it mean to add 2 vectors? Well, suppose we have 2 vectors, call them A and B. If, for example, A represents the displacement from the university to the supermarket, and B represents the displacement from the supermarket to my home, then we might want to combine them to find out the displacement from the university to my home. And the way we do this, to get the vector we get by adding, is by drawing a triangle. So I make a triangle where one side is the vector A, so there it is, and where another side is the vector B. So that's B there. And then the sum of these 2 vectors is the third side of the triangle. So in this case it looks like this, and we write it as A plus B. So clearly, in the case I mentioned of displacement vectors, this is a very meaningful thing. If this is the university to the supermarket, and this is the supermarket to my home, then A plus B is definitely how to get from the university to my home. Another thing we want to do is subtract vectors. In order to tell you how to do that, I'm going to tell you what minus a vector means. So, use B again. So now, suppose we have this vector B. The vector minus B is a vector that looks very similar, but it points in completely the opposite direction. So minus B has the same magnitude as B, but points backwards, completely the opposite direction. So this here is minus B. And then it's certainly reasonable for us to define A minus B to be A plus minus B. Let's see what that means in a triangle. So in order to define A minus B, we make a triangle where one side looks like A. That's about that vector. And a second side looks like minus B. So now this looks like this. And then the difference, what you get by subtracting the vectors, A minus B, is now the third side of this triangle. And then that again turns out to be useful for reasoning about displacement vectors and other sorts of vectors as well. I'd like to note one special case now. What happens if we subtract a vector from itself? So what happens if we take A minus A, for example? Well, then we get a degenerate triangle. So we have a triangle where one side is A, and where another side is minus A. So that second side really just lies on top of the first one. So I'll draw it on top, and that's minus A. And then the third side goes nowhere at all. So we find out that A minus A, which is A plus minus A, is the zero vector, which makes sense, just like it makes sense for ordinary numbers.